Hello, everyone. Welcome. Today, we will focus on the solubility of poorly soluble salt affected by change of the pH. We will use calcium oxalate as an example to discuss it qualitatively and quantitatively. Before we get started, I'm going to turn off the video so that we can focus on our class. KSP the solubility product constant is the equilibrium constant for the equilibrium between the ionic solid and its saturated solution. KSP, it is the equilibrium constant, K. Anything we discussed about the K, we can use here. KSP, just it is a special case between ionic solid and its saturated solution. It's this, okay? Now, let's look at, so we use calcium oxalate as an example. In this question, we have two parts. The part one, we are going to explain qualitatively, change the pH, how to affect solubility. Part two, quantitatively, to calculate the change of the pH on the solubility. Here, I choose two different pH, pH 8 and pH 4. Now, let's go to part one first. Let's go to the part one first. As you know, calcium oxalate, it is ionic compound. It is poorly soluble in water. When we dissolve it, to the water, and that one will dissociate to ions, AQ, aqueous solution, cation, and an ion. And we know oxalate or oxalate ions are weak base. Which can react with acid. To give hydrogen oxalate and hydrogen oxalate will react with acid further. To form oxalate acid, as we can see from these three equilibrium equations. At low pH, lower pH, which means stronger acid, and the chemical equilibrium the chemical equilibrium shift to the right. To the right. Now, and the more oxalate ions will form. So and this equilibrium also will shift to the right. Right. I'm going to summarize, okay? I'm going to summarize from these three equations. The lower pH, the more oxalate ion react to give hydrogen oxalate and oxalate acid, the more calcium oxalate will dissolve in water. Therefore, the solubility of calcium oxalate depends on the pH. Beautiful, very nice. We only need to write three equations, chemical equilibrium equation, and we based on the chemical shift. Nicely tell us, indeed, change the pH and the solubility of ionic compound will increase. Change the pH will change. Lower the pH and the solubility will increase. So that's the first part. Now, let's look at the second part. We are going to do the calculation. Now here, I'm going to use systematically use the mass balance and the charge balance. Step by step, discuss this question. Very detailed, okay? Yeah, please make a good notes. Now, the first step, I'm going to write here step by step, right? Step one, I'm going to write related equilibria. I'm going to write all the equilibria in the system. The first one is related to KSP. AQ, aqueous solution, that's the first one. Yeah, please pay attention to charge and also the states, solid, aqueous solution. Now, as we know, oxalate ion react with water, form hydrogen oxalate and oxalic acid. So they have two equilibria. The first one is related to K1 or Ka1. That's aqueous liquid. This equation 2. This one, it is equation 2. So let me write this better, okay? Yeah, let's erase it, write it better, okay? Hydrogen oxalate will continue react with water. Equation 3, here it's AQ. Now, always remember, this is in the aqueous solution. Water is a solvent. Equation 4. And from this equation, as we know, the first one, it is related to KSP. The second one is a Ka1. Third one, Ka2. The last one is a Kw. And KSP, Ka1, Ka2, Kw, all is a constant. Here, give it to us. So KSP, Ka1, Ka2. So we will use this constant in a minute. Okay, that's the first step. The second step, step 2. We are going to define the unknown. We are going to define the unknown. In this case, as we know, calcium oxalate, it is a stronger electrolyte, so that the molar analytical concentration, equals the equilibrium calcium ion concentration. So we define the solubility equal S, and the S equals Ca2 plus. S solubility equal Ca2 plus. Step 2. Step 3. We are going to write all equilibrium concentration expressions. We are write all. Let's do that. So based the equation 1, we have a KSP product equilibrium constant, which equals, I have it, 1.7 times minus 9. So that one is 5. Now, the second one, we are going to look at the Ka1. Ka1 based on the second equation. So which equals and we do have it, Ka1, 5.60 times 10 to the minus 2, equation 6. Now we are going to use equation 3. We are going to write a Ka2 the same way. Which equals 5.42 times 10 to the minus 5, equation 7. Now, let's use equation 4. So which is a Kw 1.0 times minus 14, 8. So any question until this point? Excellent. Let's move on. Now we are going to step 4. Step 4, we are going to use mass balance expression. Use mass balance. As you know that, because calcium oxalate is the only source of calcium ion. So that's the only source, right? But for the oxalate, there were 3 species. Let's go back. 3 species for the oxalate, which is 1, 2, 3. Can you see? 1, 2, 3, right? So that the concentration of calcium ion equals and that equation 9. So this is a mass balance. This one, it is a mass balance. Now, what do we need to do? What's this? That one equal S, solubility. Our job right now, we need to find out S equal what? We need to start it here. So let's look at how many unknown. How many unknown? Let's look at, let's count, right? So we have 4 unknowns. 1, 2, 3, 4. 4 unknowns, right? Now let's look at how many equations. How many mathematical equations? 1, 2, 3, 4. Did you see? So we have 4 unknown, 4 mathematical equations. Theoretically, yes, we should be able to solve the equation, get the solubility, molar solubility of calcium oxalate, right? Now, how can you do that? Look at this one. Look at equation 5. KSP. So we know this one is S. And if we can find out the relationship oxalate with S, and we just simply solve this equation. Now, how can we do that? We are going to convert, replace, or we convert this one, hydrogen oxalate what's the relationship with oxalate or oxalic acid? What's the relationship with oxalate? Do you follow me? Right. So then we can solve this one. Now, how are going to solve this one? How are going to solve this one? Now, how are going to solve this one? Let's go back. Let's go back at Ka2. See, let's go back at Ka2. I'm going to write it here. From here, from Ka2, do you think just to symbolize and that one C2O and the Ka2, right? So we done this one, okay? Now let's look at this one, oxalate acid. Now where we do, oh, here should there be 1 minus 1, okay, not the 2 minus, okay. I'm going to write one more time. So you are going to make a correction, okay. This is 1 minus. Now we are going to find this one. We are going to use Ka1. So see, equal what? Equal Ka1. Now, you have hydrogen oxalate. Use this one. Ka2, right? Get it? So we just symbolize and the square. You see it? Did you see it? So from this two equation, we get hydrogen oxalate, oxalate acid, hydrogen oxalate, oxalate acid, all is related to what? Oxalate. So we solve the equation, we put the back equation 9. We can do that, right? Now, question is much easier now, okay? Much easier now. Let's look at. So when pH equal 8, when pH equal 8, which means 1.00 times minus 8 molarity. So that I'm going to do the here, okay? You put 1.00 times 10 to the minus 8. So Ka2, 5.42 times minus 5. You just do the math. It's 1.585 times 10 to the minus 4. Now, the same way we calculate this one, okay? So we calculate it's a 3.30 times minus 11. You are going to do the math by yourself. Right, now I'm going to, so here it's a 10. And here it is 11. So 10 and 11 go to the 9. Which equals solubility. Plus 1.85 times minus 4 plus 3.30 times minus 11. Now you do the math. Of course, here it is 1, right? Here it's 10 to the minus 4, 10 to the minus 11. We do approximation. So do you think it just equal 1, right? Did you see? Just equal 1. Now, how are you going to do that? So we know, can you see the sample 5, equation 5? Equation 5 is what? KSP it's S solubility square equal 1.9 times minus 9. We do the math, very simple, right? Square root, you get a solubility, which equals 4.1 times minus 5. And in this pH equal 8. I'm going to highlight. It's beautiful. See, we use very simple steps. We calculate when pH equal 8, the solubility is 4.1 times minus 5, okay? So we finish the first one. pH equal 8. Now let's look at pH equal 4. pH equal 4. I'm going to write it here. I use a different color. See, pH equal 4. When pH equal 4, which means the concentration of hydronium equal 1.00 times minus 4. You see? Now let's look at equation 10. So that can we calculate to the mass the same way to do that? The same way to do that, you only change it to 1.00 times minus 4, C2O4, and 5.42 times minus 5. Right? Did you see? Now what do we have? You do the math, you will get 1.85. The same way from equation 11, the same way, you can see, the same way, you just substitute the concentration of pH 4. The same way do that. I'm not going to do that, okay? You can simply check the mass. Oxalatic acid equal what? And that one equal 3.30 times minus 3. Now, here I can say this one, it is equation 12. This one, it is 13. Now, we 11 or 12, 13 go to 9. Where is the 9? Here it's a 9. You see? Here it's a 9. Now, so you get the solubility equals, right? You equals oxalate plus 1.85 oxalate plus 3.30 times minus 3 oxalate. Now you do the math. So that should equal 2.85 oxalate. Right? So what do we have? 1 over 2.85 or 1.8 over 2.85 solubility. Do you see? Now that one we can say equation 14. Now equation 14 go to which one? Go to 5. Equation 14 you go to 5, which is a KSP right? Did you see? We get what? We get 2.85, and here it's S squared 2.85 equal what? Equal 1.7 times minus 9. If we do the math, the solubility, which equals 7.0 times minus 5 molality. Right? Now, what's this? And that one, it is a pH equal 4. In the part 1, we said when pH lower, the acidity increase, the solubility increase. Part 2, we do the calculation. I'm going to do the summary. I'm going to write it here. See these two numbers, 8 and 4. Did you see? Did you see 8 and 4? And when pH lower, acidity increase, the solubility increase. Indeed, the solubility at pH equal 4, 7.0 times -5, you divide 4.1 times -5, and that close to 1.7. 1.7 times, right? So what's it mean? What's it mean? Can you draw a conclusion for this one? Can you? Can you draw a conclusion from this one? Right? So which means 1.7 times more soluble of calcium oxalate at pH equals 4 than pH equals 8. Increase the acidity, lower the pH, the solubility increase. It's really cool. It is really cool, okay? Right? Now, let's do summary before we finish this part. We quantitatively and quantitatively discuss the pH influences the poorly soluble ionic salt. Indeed, again, calcium oxalate is 1.7 times more soluble at pH equal 4 than pH equal 8. That's the first part, right? That's the first part. You are going to make a note yourself. And the second part, we did it step by step, very detailed. So which is when we use systematic approach, mass balance, charge balance for equilibrium. And that approach, it is very useful, very powerful, which I can tell you can solve any equilibrium questions, easy one or challenging one. And lastly, let me know if you have any questions or need any help. You can always email to me, text to me. Thank you. I will see you next time.